Hello, good day. You are welcome to our class for today. So today we are still going to be discussing heat energy measurement. That's what we are going to discuss in this class. Now, this lecture will cover specific capacity by method of mixtures. That is how you can calculate specific heat capacity by method of mixtures. Then also specific heat capacity by using the calorimeter. Then heat energy by electric from an electric source. Then we'll also do some calculations. Remember that we've already treated some areas of heat energy measurement where we discuss specific capacity and heat capacity. So for today's class, we'll look at specific capacity by method of mixtures, specific heat capacity by the calorimetry method, and heat energy from electrical source. Okay, so this is Normal Science Tutors Online. If you are not subscribed to our channel, please subscribe to this channel, click on the notification bell so that when we upload a new video, YouTube will notify you. And also invite your friends so that they can come and enjoy the class that you are enjoying. You can reach us through the WhatsApp number that is showing right on your screen. So that's okay. So please get your writing materials so that we can go straight to the class for today. Heat energy measurement, heat capacity by the method of mixtures. So let's go. Okay, so we have discussed heat capacity before, and we've said that quantity of heat is equals to mc theta, right? We said that quantity of heat is equals to Q is given to you to be mc theta, where m is mass of the substance, c is the specific capacity, and theta is the change in temperature. Okay, so for you to determine specific heat capacity using the mixture method, you normally the calorimeter is used, right? The calorimeter is used. The calorimeter is an instrument that you use to measure the quantity of heat. Okay, so we have different types of calorimeters. We have the bulk calorimeter, glass calorimeter, and then the ice calorimeter, as the case may be. Now, in the calorimeter, what is done is that a liquid substance, mostly liquid, is placed in the calorimeter. Then the temperature of the liquid and that of the calorimeter they are taken. Then you now transfer a hot object into that liquid rapidly. Then you begin to stir continuously until you get to a uniform temperature. When you have a constant temperature, then you also take that temperature. That will be the final temperature of the hot object, the calorimeter, and the liquid that was inside the calorimeter. Is that okay? So a hot substance, solid or liquid, is added to a cool substance, and the liquid stirred until everything attains the same temperature due to energy transfer. Now, when you have done this, we can state that, okay, so you can make this statement that the heat lost by the hot substance is equals to heat gain by the cool substance. If we neglect energy loss to the surrounding and all that, this is a statement that holds. Okay, so talking about conservation of energy, so no energy is lost to the surrounding except between the mixture and the hot substance. I mean between the cooled body and the hot substance and the calorimeter. So this statement holds that heat lost by hot substance is equals to heat gain by the cold substance. Now we've said that quantity of heat is equals to Q. So we can actually represent for the hot substance, we can write it as QH. QH equals to MC theta. Okay. Then the one for cold, we can write it as QC, quantity of heat for cold substance, the same thing as MC theta. Okay, so there is something that I want you to take note of, that for the hot substance, the initial temperature can be written as theta H, then you know that the temperature of the calorimeter and that of the cold liquid that we are on it, they are the same. Okay, so the initial temperature, what you want to take note of is that the initial temperature of the calorimeter and the cold liquid, they are the same. But in this particular instance, we are not even going to look at the calorimeter yet. We are going to treat that of the calorimeter. But for in this case, the initial temperature of the cold substance is given to you as theta C. This initial temperature of the cold substance, this initial temperature of the hot substance. Note that after mixing the two together, the cold substance and the hot substance, they will now have what? The same final temperature. So that when you are looking for the temperature change for the hot substance, it will be its initial temperature of theta H minus their final temperature. So this is, say, temperature change for the hot object is equals to the 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 final temperature, okay, the initial temperature, which is hotter than the final temperature. Then for the cold objects, for the cold liquid, it is the final temperature minus its initial temperature, so if I put this as final temperature and 0 as initial temperature, this will now be this. Then if this is this, we can have this too. So these are the temperature change for the hot object and then the cold body. Okay, so if we come back to what is written here, so that the temperature change of the hot substance is equals to the initial hot temperature minus the overall final temperature, and then the temperature change for the colder substance is equal to final temperature minus its initial temperature. So having known that, we can now begin to look for the quantity of heat. So quantity of heat lost by hot substance equals to mc theta. The C is the heat capacity, m is the mass, and theta is change in temperature, which is equals to this. Then the heat gained by the cold substance, the same mc theta, the mass of the cold substance, the specific capacity, and then the change in temperature. So we can now do this, do this equation from heat lost by hot substance equals to heat gained by cold substance. We can have this relationship. Is that okay? Then finally we come to this equation. Okay, so this is how to, you can use this one now to find, from this equation you can actually find either the final uniform temperature, or depending on the variable that you are asked to look for, you can look for it from this particular equation. So take note of this equation. Is that okay? Just take note of it, because we are going to apply it to solve some problems. Now let's look at heat capacity by the calorimetry method. Okay, by the calorimetric method, just like what we said before now, in this particular instance, you are going to put into consideration the heat absorbed by the calorimeter, because the heat given out by the cool body will be equals to the heat gain. This heat lost by the hot substance is equals to heat gain by the calorimeter plus heat gain by the cold substance. We know that the cold substance is inside the calorimeter, so they have the same temperature. Okay, so you can say that quantity of heat lost by the hot substance equals to quantity of heat gained by the calorimeter plus quantity of heat gained by the hot substance inside the calorimeter. Now, what you should know is that the initial temperature of the calorimeter and the cold substance inside of it, they are the same. And besides that too, their final temperatures of all the substances, they are all the same. Okay, their final temperatures are all the same. So if you have that, that is so, then the change in temperature for the hot substance will be its initial temperature minus the overall final temperature. Then for the calorimeter, or for the cold substance it will be the final temperature minus the initial temperature, and then for the calorimeter is also final temperature minus the initial temperature. Take note that these two initial temperatures, they are the same. I just made it like this for clarity. So having said that, you can now say that heat lost by the hot substance is equal to mc theta, which is theta is change in theta, which is the change in temperature. The heat gained by the cold substance is mc theta, change in temperature. Heat gained by calorimeter is equal to mass of calorimeter than the specific capacity times change in temperature. Then you cannot have this equation, you cannot equate them together. Heat loss by the hot substance is equal to heat gain by calorimeter plus heat gain by the cold substance. I said, and note, the initial and final temperature of the calorimeter and the cold substance are the same. Hence, their change in temperature remains the same. So, which means that the change in temperature for the calorimeter and the change in temperature for the cold substance, they are the same. They are the same. They are not different. Okay, so if you have taken note of this, we can now solve some problems for you to have a deeper understanding or how to apply this equation, because sometimes when you are looking at this equation they look a little bit confusing, but if you apply them to solve a problem you begin to understand them deeper. So let's solve some problems now so that you can understand how to apply the equation that we have discussed so far, right? So this is a sample question. I want us to look at it critically so that we'll know how we got all the temperature changes. Okay, so this one says calculate the final equilibrium temperature. Okay, calculate the final equilibrium temperature if the mixture of 250 grams of water at 65 degrees centigrade, note, is added to 150 grams of cold water at 5 degrees centigrade. Neglect heat absorbed by the surrounding. Specific capacity of water is equals to this. The first thing that you need to do here is to understand the question. If you can understand the question, it becomes easy. This is the temperature of hot water. This is the temperature of cold water. Now these two, they are mixed together to attain a final temperature, and that is what you are looking for. This is the mass of the hot water and this is the mass of the cold water. So from our equation that we just wrote, we said that the heat lost. Okay, so let me say QH. If I represent QH by hot water, so quantity of heat lost by hot water is equal to the heat gain by cold water. Okay, so this we are given in this particular question, we are given that mass of, and this quantity of heat is equals to mc theta for hot water is equal to mc theta for cold water. Okay, so let's have this at the back of our mind. Then let's go and bring out these variables that are given. We are given that mass of hot water is equal to 250 gram. Okay, so you can actually convert this to kg to give you 0.25 kg. 0.25 kg. Then the temperature of the hot water, let me put it at theta h is 65 degrees. This is the initial temperature of the hot water. Okay, then for the cold water, the mass of cold water, mc, and just put it at that, is 150 gram. Okay, so this you can convert to kg too to give you 0.15 kg. Okay, then you are giving the initial temperature of the cold water is given to you to be 25 degrees centigrade. Please take note of all this. Then we are given that the heat capacity, specific capacity of water is equals to 4200 joule per Kelvin by kgK per Kelvin. Fine. So these are the variables that are given to us. We want to put all these variables now into this equation. What is not given to us is final temperature theta. So this one I put a question mark there. Okay. So having known all this, now the change in temperature for the hot water, change in temperature, let me say change in temperature for hot water, change in temperature for hot water now is equal to, this is your final temperature, which you don't know. And as I said, for mixtures, the final temperature of the cold water and the hot water, they are the same. So which means that this will be the final temperature for the hot water. So it will be the initial temperature, which is 65 minus final temperature, 65 minus theta. Okay. Then for the cold water, the temperature change will be equal to the final temperature minus 5 degrees. Note that the final temperature will be higher than that of the initial temperature for the cold water. So take note of these two temperature changes. This is how you calculate their temperature changes. The temperature change for the cold water, the final temperature for the cold water will be higher than this initial temperature, while the final temperature for the hot water will be lower than its initial temperature, and that's what we have here. So we can bring all this one into this equation. So we're going to have that the heat loss by the hot water will be the mass of the hot water, which is 0.25 multiplied by the heat capacity of water multiplied by their change in temperature. So the change in temperature for the hot water is equals to what? We say 65 minus theta. Okay. Then for the cold water, the mass of the cold water is 0.15. This is also multiplied by the heat capacity of water multiplied by their change in temperature for the cold water is final temperature minus its initial temperature. Okay, so once you have gotten this, to solve the problem becomes easy, right? To solve the problem becomes easy. It's heat loss all over heat gain. I mean, heat loss is equals to heat gain. So once you have written this out, it becomes easy. Just work it out. You see, these heat capacities will cancel out. Yeah, we can just cancel those ones out first so that to make everything less clumsy. Okay, so we can make everything less clumsy so that we have 0.25 multiplied by 65 minus theta all over 0.15 multiplied by theta minus 5. Fine. So from here now we can progress easily. If you want to work all this one out, this will give you 16.25 minus 0.25 theta is equals to 0.15 theta minus what? 0.75. Okay, so guys, just work this out. We'll take like terms, collect what like terms to both to two different sides, so that you have 16.25 plus 0.150 equals to we have, okay, that's plus 0.75 0.75 equals to 0.15 theta plus 0.25 theta. Okay, so when you work all this out, this will give us 17 is equals to 0.4 theta. So you make your theta the subject of formula, final temperature. So you have 17 over 0.4. And by the time you work this out, you have that your final temperature is equals to 42.5 degrees centigrade. So this is your final temperature. Now, what I want you to take note of is this temperature change, because in most cases, that is where students have problem. How you can get this temperature change. Remember that for the hot objects and the cold body, at the end of the day, they are going to attain the same final temperature. Now, the final temperature for the hot object should be less than its initial temperature, and then the final temperature for the cold object should be higher than its initial temperature. So if you understand that, you can easily get the temperature change. Once you have gotten the temperature, the remaining thing is just for you to use your MC theta, MC theta. Heat loss by hot body is equal to heat gain by cold body, and then the whole thing is to do your little mathematics, and then you get to your final answer. Okay, so I hope this one is clear and understood. Okay, so thanks. So let's go to another one so that all right, so this one is also another sample question that we can solve too. Another sample question. It says that hot water is added to 4 times its mass of water at 25 degrees centigrade and thoroughly stirred. If the final temperature of the mixture is 40 degrees centigrade, calculate the initial temperature of the hot water. Okay, so this one is like turning it round from the first questions that we solve, but the principle remains the same. So just follow the same principle, that quantity of heat lost by the hot water is equal to quantity of heat gained by the cold water. So MC theta for hot water is equals to MC theta for cold water. Now for this, since everything is water, the heat capacity can go. Okay, so let's bring out what is given to us. Said mass, if mass of hot water is equals to mh, m of hot water is equals to m, then the mass of the cold water will be equals to what? It's equals to 4m. Because that is what the statement says, that hot water is added to 4 times its mass of water at 25 degrees. So this is the mass of cold water, this is the mass of hot water. Then you are giving the final temperature of the mixture. So if for the hot water, initial temperature for hot water is unknown, that is what we don't know. Then final temperature for the two, let me put it as theta is equals to 40 degrees. That is for the hot and cold water. The initial temperature for the cold water is given to us to be 25 degrees centigrade. So which means temperature change for hot water, say temperature for hot water, temperature change for hot water will be equal to its initial temperature that we don't know minus the final temperature. Then temperature change for cold water will be equals to 40 minus 25, which is already known. So 40 minus 25 is equals to what? Is equals to 15 degrees. So this is the temperature change for cold water. right? So I haven't known all these variables now. Let's put them now into this equation that we have, that heat loss by hot water is equals to heat gain by cool water. So mass of hot water is equals to M times the temperature change for the hot water is equals to theta H minus 40. Then for the cold water, the mass of cold water is 4m multiplied by the temperature change of cold water is 15. Okay, so we can just solve this out now. But before we do, this mass, they can cancel each other out. Okay, so if they cancel each other out, we are going to have the initial temperature of hot water minus 40 is equals to 4 times 15. 4 times 15 is equals to 60. Okay, so the temperature will be equals to, if you add 40 to both sides, to be 60 plus 40. So that will now give us 100 degrees centigrade. Okay, so that is what we are asked to find. This is now the initial temperature of the hot water. You see, so the most important thing for you to be able to bring out these informations, once you can bring out these informations, you apply them into this equation, your answer will just come out readily. Okay, so I hope this one is also understood. Please, you can pause the video and also listen to it repeatedly so that you will understand better. Pause the video, you can repeat it so that you understand better. Let's solve one more problem again. Okay, so this is another question that we need to solve, and this one has to do with the calorimeter. Okay, so this one says a piece of copper of mass 0.1 kg is heated to 100 degrees centigrade and then transferred to a well-lard copper calorimeter can of mass 0.05 kg containing 0.25 kg of water at 10 degrees centigrade. Calculate the final steady temperature of the mixture. You are given specific capacity of water to be this, and specific capacity of water and calorimeter to be of copper to be 400 joule per kg K. That of water is 4,200 joule per kg K. Okay, so these are the variables that you are given. Now, from our discussion initially, we said that quantity of heat lost by the hot object, say quantity of heat lost by the hot object, QH, I represent that by QH please, is equals to the quantity of heat gained by calorimeter, I represent that by QCal, plus the quantity of heat gained by, let me say, the liquid that is in there. I put it as liquid. The liquid could be water, it can be any other liquid, so that's why I say liquid. Okay, so this is the equation that we had. Neglecting heat loss to the surrounding, this is the equation that quantity of heat loss by the hot object equals to quantity of heat gained by calorimeter plus quantity of heat gained by the liquid. So this one is equals to mc theta, this change in temperature for the hot object, is equal to mc theta for calorimeter plus mc theta for liquid. Okay, so the calorimeter and the copper, they have the same specific capacity. Okay, fine. So from here now, let us bring out all these variable. One, mass of copper mc is given to you to be 0.1 kg. Fine. The initial temperature, let me see, temperature of copper or for hot objects, initial temperature C is equal to, that is for hot object, initial temperature is equals to, it's given to us to be 100 degrees centigrade. Okay, mass of calorimeter mcal 0.05 kg. Initial temperature of calorimeter qcal, let me just put it at that, is 10 degrees centigrade. Mass of liquid is equals to 0.2 kg. Okay, initial temperature of liquid, let me say theta L is equals to the same 10 degrees centigrade. What did they ask us to find? So to find the final temperature theta of the mixture. Okay, now you are given heat capacity of water, heat capacity of copper. So we'll take that from that equation like that. Alright, so the important thing I want to first of all bring out here is the temperature changes. Okay, so for the hot object that is brought, the temperature change will be equal to 100, which is the initial temperature, minus the final temperature, which is theta. Remember that the final temperature of the hot object will be less than its initial temperature. Then for the calorimeter, the temperature change for calorimeter, let me put it like Tcal is equals to theta minus 10. Then that of the hot water to temperature change, I mean for the cold water, let me say T liquid is equals to theta minus 10. Now if you look at it, you find out that temperature change for calorimeter and cold water, they are the same. Their initial temperatures, they are also the same. Is that okay? So once you have been able to bring out all this, it becomes easy. Just substitute them into this equation that you have. So for this, we have the mass of the copper is 0.1 times 400, which is the heat capacity of copper, specific capacity of copper, multiplied by the change in temperature. So the change in temperature of copper is 100 minus theta. Then is equal to the mass of calorimeter 0.5 multiplied by heat capacity of calorimeter, which is 400, times temperature change, which is theta minus 10, plus mass of water is 0.2 multiplied by the specific capacity of water times the temperature change of water, which is also theta minus 10. Okay, so this is your equation. You have written everything. Once you have gotten to this stage, the problem is solved already, right? So you can do your multiplication out and then you will get to your solution. So this one will give you, if you multiply all this out, your answer will come out readily. 0.1 times 400 is 40. So this will give us 40. 40 times 100 will give you 4,000 minus 40 theta. Okay, is equals to 0.05 times 400 is 200. So you have 200 that will be 200. You have 20, this will give us 20 first, so let's do that. 20 theta minus 20 times 100 is 200. Okay, plus 0.2 times 4,200 is equals to 840. So we have 840 theta, 840 times theta, then minus 8,400. That's 840 times 10 will give you 8,400. Okay, so let me just clean some places here so that I will have that space. Alright, so thanks. So once you have gotten this now, begin to collect your items together. Okay, collect your items together. Do your addition, collect your items together so that your answer will come out readily. So that your answer will come out readily. Okay, so here you are going to have 4,000 minus 40 theta will be equal to 20 plus 840 is 860 theta minus 8,600, because minus 200 minus 8,400 is 8,000 is minus 8,600. Okay, so now you can collect your items, collect the theta together, and then the whole numbers. When you collect your items together and then your whole numbers, you have 4,000 plus 8,600 equals to 860 theta plus 40 theta. 40 theta. Okay, so this will give you 1,000 or 12,600 equals to 900 theta. So you make your theta the subject of the formula so that you have 12,600 divided by 900. Okay, so by the time you work this out, cancel this 0, 0, you are going to have that. You are going to have 14 degrees centigrade as your final answer. So this is the final temperature of the mixture. So this gives you the final temperature of the mixture. Is that okay? So the main area you want to look at is this part of trying to get the temperature change. Okay, where to get the temperature change, this is the part that you really need to look at very well so that you will not make any mistake. Once you are able to get this part correctly, just apply this equation, mc theta, mc theta, mc theta, and then your answer will come out readily. Alright, so I hope this is clear. Please, you can replay the video to give you a more better understanding. Alright, so sometimes you can also use electrical means to get your quantity of heat generated. Okay, so if you are using electrical heater, the quantity of heat or heat energy from electricity is given by the quantity of current times the potential difference times the time taken. Okay, so this is quantity of heat from electricity, and then we know that power is equals to energy over time. So which means that energy is equals to power times time. I hope this is clear. Okay, so you can actually depend on the equation that you are giving, you can actually use this power times time. Power times time equals to heat energy, which equals to mc theta. Or you can use any of this IVT which is heat energy from electricity, is equals to mc theta. So depending on the equation that you are given, you can apply any of this equation to solve when it has to do with electrical energy. Okay, so having said that, we can just solve some problems for you to understand this better. So let's solve a problem. Okay, so this is a sample question that I want you to look to. It says an electric heater rated 15 volts 40 watts fitted into a metal block supplies heat to the block of mass 1.5 kg and specific capacity 460 joule per kg per Kelvin. Calculate the change in temperature if the current flows for 10 minutes. So as we discussed earlier, we said that power times time is equals to mc theta. So for this particular problem, you are giving power to be equals to 40 watts. Then you are giving time to be 10 minutes. So just convert this time to seconds multiplied by 60. Okay, so that will give you 600 seconds. Fine. Then mass of the block is equals to that power heat is transferred to is equals to 1.5 kg, and the heat capacity is given to you to be 460 joule per kg K. Okay, so I haven't gotten all this. Let's substitute all this information now into temperature change is not given to you. That's what you are looking for. So if you substitute into this equation, we're going to have that power is 40 times 600, which is the time in seconds. You know that we got the 600 from 10 times 60. Then times is equals to mass times heat capacity times temperature change. So from here, temperature change will be equals to 40 times 600 all over 1.5 times 460. So temperature change, which we are looking for now, will be equal to what? When you solve all this one out, you are going to have 34.78 degrees centigrade. So this is how to use electrical power or electrical energy to solve problem. When it has to do with electrical energy, this is how to go about solving them. This one has to do with power. So let's do another one that does not have to do with power very quickly. So this is another question. This one does not have to do with power, but it has some other elements. You have current, you have the potential difference, and then here you are asked to find the time. So how long will it take to heat 3 kg of water from 28 degrees to 88 degrees in an electric heater taking a current of 6 amps from an EMF source of 220 volts? So just as we said, heat energy from electricity, heat energy is given by either IVT or is equal to IV is power or P times T. Okay, so but in this instance here we are giving current, you are giving V. It is time that you are giving, you are not giving. So this equation with now is what we will apply. So we are going to apply IVT is equal to mc theta. Fine, so let's bring out the variable. The mass of the water is 3 kg. Temperature change is given to us to be 88 minus 28. 88 minus 20 is equals to 60 degrees. Oh, that's correct. You are giving current I to be 6 amp, and potential difference V is equals to 220 volts. T you are not giving. So substituting into this equation, we are going to have 6 times 220 times time equals to mass 3 times heat capacity of water is 4200 times temperature change, which equals to 60 times 60. Okay, so if you make your T the subject of this formula, we are going to have that 3 times 4200 times 60 all over 6 times 220. So if you solve all this out, you have your time to be equals to 572.7 seconds. Okay guys, so we have solved a lot of problems in this topic, and I hope that they are clear. Okay, so please just go through these questions very well so that you have a deeper understanding. All right, so this is your test page. Please solve all these problems. You can post your answer or the WhatsApp number that is showing on your screen. I will look at them and then give my own comments. That's okay. If you have any challenge, you can also let us know. But before we go, if you have not subscribed to this channel, please subscribe to this channel. Give us a like if you like what we are doing. Give us a thumbs up. Click on the notification button so that when we upload a new video, YouTube will notify you. Reach us through the WhatsApp number that is showing on your screen. This is No Man's Science Source Online, and we are bringing physics direct to your very home or to your very doorstep. So thank you for your time. Invite your friends so that they can come and enjoy what you are enjoying on YouTube. Thank you. We'll see you on our next video.